There are traces in the universe that come from its first seconds of life. This audiobook invites you to explore the fossil waves, subtle traces in space-time and in the oldest light which still retain the echo of the birth of the cosmos. What can they tell us about that initial moment when everything began? A journey to the universe's oldest scars, where every pattern and every ripple is a message from the origin. Fossil waves allow us to glimpse the first moments after the Big Bang, when everything we know began to take shape. Did you know that in the first moments of the universe's existence, everything was concentrated in an incredibly small and hot point? From there, a monumental explosion gave rise to the expansion of space and time. Fossil waves are, in a sense, the echoes of that event, a whisper from the past that still resonates in the present. How can we listen to these echoes? Through cosmic background radiation, a form of light that fills the universe. This light is like an old photograph, captured at the moment when the universe cooled enough to allow light to travel freely. Fossil waves are the traces of that primordial light, and by studying them, we can unravel the secrets of how the first structures in the cosmos formed. Now, we may ask ourselves, why are they so relevant to us? Fossil waves are not just a relic of the past, they are a key to understanding the processes that shaped everything we see today. Stars, planets, and galaxies. Without these waves, our understanding of the universe would be like a book with missing pages, unable to tell the complete story. As we explore fossil waves, we encounter a series of intriguing questions. How did the first particles organize? What role did they play in the creation of galaxies? These questions lead us deeper into the cosmic journey, where each answer opens the door to new inquiries, like a labyrinth of knowledge that expands as we explore it. The importance of fossil waves lies in the fact that they offer us a window into the past, a unique opportunity to observe how the universe has evolved. As the waves move through space and time, they bring us information about the conditions that prevailed in the early universe. It's like listening to the echo of a melody that was played billions of years ago, allowing us to understand the cosmic orchestra that gave rise to our home. But how are these waves detected? Throughout history, scientists have developed ingenious methods to capture this radiation. From telescopes that observe the sky in specific wavelengths to sophisticated satellites floating in space, each tool brings us a little closer to deciphering the mysteries of fossil waves. It's like being detectives of the cosmos, using every clue to piece together the puzzle of the universe. It's fascinating to think that the key to understanding how the universe formed lies in this tiny, faint radiation. Every little flicker we perceive speaks to us of the history of our cosmos. But what are the special characteristics of these waves? This is where quantum physics comes into play, revealing a world where the rules are different from those we know in our daily lives. The often perplexing quantum interactions offer us clues about the very nature of the universe. As we delve into the meaning of fossil waves, we also find fluctuations in the density of the early universe. These small irregularities are like bubbles in a boiling liquid, which, as they cool, become the seeds of galaxies. Without these fluctuations, the universe would be a very different place, with an empty and lonely cosmic landscape. The large-scale structure of the universe as we know it today is also influenced by these fossil waves. Galaxies and clusters of galaxies are distributed in patterns that can be traced back to the small perturbations in cosmic radiation. It's as if fossil waves are tracing an invisible map that helps us navigate the vast ocean of the cosmos. Moreover, the theory of cosmic inflation, which suggests that the universe expanded exponentially in its early moments, is intrinsically linked to fossil waves. This theory helps us understand why the universe is so homogeneous yet so diverse. Fossil waves provide us with tangible evidence of this inflation, a testament to the dizzying growth that our universe experienced in its infancy. As we explore the evolution of fossil waves, we see how they have changed from the Big Bang to today. They are witnesses of time, capturing the history of a constantly transforming universe. Each new discovery brings us one step closer to deciphering the enigma of how everything began. Dark matter and dark energy also play a crucial role in this narrative. Dark matter, that mysterious substance we cannot see but which influences gravity, affects how fossil waves are distributed in space. Dark energy, on the other hand, is responsible for the accelerated expansion of the universe. And its interaction with fossil waves is a field of research that is still evolving. Finally, the exploration of fossil waves is not just a journey through the history of the universe, but also a reflection on our place within it. Each discovery invites us to question and marvel, to recognize that we are part of a story much larger than we can imagine. Fossil waves are, in essence, a reminder that the universe is a place full of surprises, where every answer generates new questions and inspires us to continue probing the mystery of the cosmos. What if I told you that everything we know today, from the stars that shine in the sky to the Earth we live on, has its origin in an incredibly intense and hot moment? That moment, known as the Big Bang, is the key to understanding the birth of the universe. In a fraction of a second, everything that exists was created from a singularity, a point of infinite density and temperature. But how do we unravel the secrets of that primordial instant? Imagine an explosion of energy that gives rise to everything we know. In the first moments after the Big Bang, the universe was an extremely hot and dense place. Particles like electrons and protons were so close to each other that they could barely move. It was chaos in which light could not even travel. But as the universe began to expand, something extraordinary happened. The temperature started to drop, allowing particles to come together to form atoms. Now, what happened after the atoms were formed? The conditions of the universe changed rapidly. As it cooled, hydrogen and helium atoms joined together and began to form the first stars and galaxies. Imagine a vast ocean of gas that, as it cools, starts to form luminous islands. These islands, or galaxies, are what we can observe in the sky today. But how do we know that all of this really happened? This is where cosmic microwave background radiation comes into play, a kind of echo of the Big Bang that still resonates in the universe. This radiation is like a fingerprint of that initial moment, tangible evidence of what occurred in the early moments of the universe. By studying this radiation, scientists can look back in time and reconstruct the history of the cosmos. But how can something from such an ancient event be detected? Through powerful telescopes and satellites? Scientists have been able to measure this radiation at different wavelengths. Technology has advanced so much that we can now see the universe as it was when it was only a few 100,000 years old. To put it in perspective, imagine looking at a photograph of a newborn baby. That image gives you an idea of what that person will be like in the future, but it also shows you the potential they have. In this way, cosmic microwave background radiation shows us the state of the universe in its early moments. And what about the small fluctuations in that radiation? Those variations are like small waves on a calm lake. These waves tell us that the universe was not uniformly distributed. There were small differences in the density of matter. Those tiny irregularities were crucial, as over time they became the galaxies and structures we see today. Without those fluctuations, the universe would be a very different place, a vast empty expanse instead of a cosmos full of life. When talking about the Big Bang, it is also important to mention how this initial explosion laid the groundwork for everything we know. The fundamental forces of nature, such as gravity and electromagnetism, began to take shape. Thus, the ingredients for the existence of matter and stars were established. But what are the implications of all this for us? The inhabitants of this vast universe. Every star we see in the sky, every planet we orbit, and even the human being itself is the product of a universe that has been constantly evolving since the Big Bang. In a way, we are all children of that primordial explosion. But as we look up at the sky, we not only see our past, we also face questions about our future. Where is the universe headed? Will it continue to expand forever? Or will there come a time when everything collapses again? Human curiosity has led us to explore these questions through science and philosophy. The search for answers about the origin and evolution of the universe is an endless journey. From the moment the first particles were formed to the creation of the first stars, each step has been a miracle of nature. So when you think about the Big Bang, remember that it is not just an event in the history of the universe, but a starting point for everything we are and everything we know. The wonder of cosmology invites us to look up at the sky and ask ourselves, what else will the universe reveal to us? What secrets remain to be discovered in the waves of cosmic microwave background radiation? The answer, though still to be unraveled, leads us to reflect on our place in the vast scheme of the cosmos. In summary, every time we contemplate the stars, we are looking back in time to a moment when the universe began to take shape. That connection to our past is a fundamental part of our existence, a reminder that we are all part of something much larger. Thus, the story of the Big Bang and its consequences remains a fascinating and ever-evolving narrative that invites us to continue exploring and learning. If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey. Fossil waves are like whispers from the universe's past, echoes that reach us from time immemorial. But what exactly are these waves and why are they so crucial for our understanding of the cosmos? The answer lies in the very history of the universe's creation. At their core, fossil waves are disturbances in space-time that were generated shortly after the Big Bang, when the universe was an extremely dense and hot place. When thinking about the Big Bang, it's easy to imagine it as a loud and chaotic explosion. However, what really happened was a rapid and violent expansion of space itself. During that primordial moment, subatomic particles formed, and over time, these particles grouped together to form atoms, creating an environment conducive to life as we know it. In this context, fossil waves emerged as an indelible trace of that crucial moment. Fossil waves are the result of variations in the density of matter in the early universe. As the universe expanded and cooled, these small irregularities became the seeds of what would later become galaxies and cosmic structures. But how can we know that these waves exist? The key lies in the cosmic background radiation, a kind of echo that dates back to that primordial time. Imagine you are at a calm lake. If you throw a stone, the waves propagate across the surface of the water. Similarly, the Big Bang sent waves through the cosmos, creating a pattern that we can still detect today. This radiation, which fills the universe, appears in the form of microwaves and is a testament to a universe in its early moments. But why is this radiation so important? By studying fossil waves and cosmic background radiation, we have the opportunity to look back in time to the moment when everything began. It's like opening a window to the universe's past, allowing us to glimpse how the first structures formed and how the cosmos began to take shape. But what is the specific role of fossil waves in all of this? Fossil waves are like an ancient map, revealing the history of the universe. Every small detail in the pattern of these waves offers us clues about the composition of the universe, the distribution of matter and energy, and even the fundamental laws that govern it. Through the investigation of these waves, scientists have been able to validate theories about the origin of the universe and better understand its evolution. Imagine you are solving a giant puzzle. Each piece you fit represents a finding about fossil waves and their relationship with cosmic background radiation. The more pieces you complete, the clearer the image of the universe becomes. However, this process is not simple. Fossil waves are subtle, and their detection requires sophisticated techniques and a meticulous approach. One of the wonders of fossil waves is that they provide us with information not only about the past, but also about the future of the universe. By understanding how these waves formed and evolved, we can make conjectures about the fate of the cosmos. Will it expand forever or collapse again? Fossil waves are, in a sense, the timelines of the universe, tracing a path from the Big Bang to the present. The study of fossil waves also leads us to reflect on the very nature of space and time. It confronts us with deep questions. How does matter and energy behave on such large scales? What does time really mean in an expanding universe? These questions invite us to explore not only the physical universe, but also our own perceptions and understandings. Moreover, fossil waves are a reminder of the interconnectedness of the cosmos. Everything is related, from subatomic particles to distant galaxies. Understanding fossil waves is ultimately about understanding our place in the vast universe. It is a journey of discovery that takes us beyond the boundaries of science and invites us to consider our role in the grand scheme of things. As technology advances, our capabilities to detect and study fossil waves also improve. New telescopes and space missions are constantly being developed, allowing us to obtain more precise and detailed data. With each discovery, we get a little closer to unraveling the mysteries of the universe and understanding how everything we know was formed. The story of fossil waves is, in many ways, the story of humanity itself. In seeking answers about the cosmos, we are also seeking answers about ourselves. Fossil waves are a mirror reflecting our innate desire to understand the world around us and our place in it. Thus, each finding about these waves is not only a scientific advancement, but also an opportunity to reflect on the human condition and our role in the vast universe. With each new discovery, fossil waves remind us that the cosmos is a place full of mysteries to solve. Every question we answer opens the door to new questions, and in this vast ocean of knowledge there is always more to explore. So the next time you look up at the starry sky, remember that fossil waves are the echoes of an ancient past, waiting to be deciphered and understood. Cosmic background radiation is one of those concepts that, at first, may seem somewhat abstract, but it is actually fundamental to understanding the universe. What is this radiation and why is it so important? To answer this, let's go back in time, right to the moment when the universe began to expand after the Big Bang. At that instant, everything was extremely hot and dense, but as the universe expanded, it began to cool. This cooling allowed the first particles, such as electrons and protons, to form, and eventually, hydrogen and helium atoms. Now imagine that the universe in its early moments was like a hot, dense soup. As it cooled, it became possible for photons, the particles of light, to start traveling freely. Before this moment, those photons were trapped, constantly bouncing between particles. But when the universe cooled enough, those photons were able to escape. This event, known as recombination, occurred approximately 368,000 years after the Big Bang. It is at this moment that cosmic background radiation is released into space. So, what exactly is cosmic background radiation? It is a form of electromagnetic radiation that fills the entire universe. It can be imagined as an echo of the Big Bang, a kind of whisper that has traveled through the cosmos for billions of years. Today, this radiation is detected in the form of microwaves, which means it is at a much longer wavelength than the visible light we can see with our eyes. In fact, if we had a suitable detector, we could perceive this radiation as a faint hum in the background, like the sound of an old television that is not tuned to a channel. The discovery of this radiation was not immediate. It was in 1956 when Arno Penzias and Robert Wilson, two physicists working in a laboratory in New Jersey, accidentally stumbled upon it. At first, they thought the signal they were receiving was a technical problem, perhaps background noise from their equipment. But after investigating, they realized they were detecting this cosmic background radiation, which earned them the Nobel Prize in 1978. This finding was crucial as it provided one of the first observational proofs of the Big Bang and revolutionized our understanding of the universe. Now, when talking about cosmic background radiation, it is essential to understand its temperature. This radiation has an extremely low temperature, around 2.73 degrees Kelvin, which is so cold that it seems almost like a vacuum. However, we should not confuse this with the absence of energy. In fact, this radiation is present in every corner of the universe, meaning we are constantly surrounded by it. It's as if the universe is whispering stories from the past. Stories that can reveal much about its formation and evolution. One of the most intriguing features of cosmic background radiation is the small fluctuations it presents. Imagine a calm surface of water, where suddenly some drops fall. These drops create waves that disturb the surface. Similarly, the small variations in density that occurred in the early universe generated those fluctuations in cosmic background radiation. These variations are vital because they are the seeds from which all the galaxies and structures we see today formed. Through studies of cosmic background radiation, astronomers have been able to map these fluctuations across the sky. This has allowed scientists to better understand how galaxies are distributed in the universe and how they have grouped over time. Thus, cosmic background radiation is not just an echo of the past, but a tool that helps us unravel the secrets of the cosmos. But what if I told you that these small variations also tell us something about the nature of matter and energy in the universe? Cosmic background radiation is closely related to dark matter and dark energy, two mysterious components that make up most of the universe. As we delve deeper into the study of this radiation, we also begin to glimpse the role that dark matter plays in the formation of structures and how dark energy is accelerating the expansion of the universe. The importance of cosmic background radiation transcends simple observation. It gives us a direct glimpse into the early moments of the universe, a time that would otherwise be inaccessible. Every measurement we make, every small detail we discover brings us one step closer to understanding how everything we see around us originated. Thus, cosmic background radiation is like an ancient book whose pages are filled with crucial information that we are still learning to decipher. In conclusion, cosmic background radiation is not just a scientific curiosity. It is one of the keys that allows us to open the door to the history of the universe. By studying its origin, its discovery, and its impact, we embark on a journey that leads us to better understand not only how the cosmos formed, but also the place we occupy within it. Through this radiation, the universe shares with us its deepest secrets, inviting us to continue exploring and discovering what still remains to be learned. Fossil waves are like echoes from the past that resonate in the vast universe. But why are they so important, and what do they tell us about the formation of the cosmos? To understand this, it is necessary to dive into the very history of the universe. Imagine that the universe is a great book, and the fossil waves are the first pages written in a language that we are just beginning to decipher. Since the moment the Big Bang occurred, the universe has been in constant expansion and evolution. Fossil waves are a type of radiation that allows us to see what was happening in those initial moments when the cosmos was an extremely hot and dense place. It's as if we had a time machine that lets us look back at a period when everything was just beginning. But what specific details do these waves reveal to us? Each fossil wave contains information about the temperature and density of the universe in its early moments. Just as the waves of the sea can tell us about the strength of a past storm, fossil waves speak to us about the energy and conditions that existed when the universe was still a baby. This information is crucial for scientists as it helps them build more accurate models of how the universe has developed since then. By observing fossil waves, scientists can answer intriguing questions. What type of matter and energy existed in the early universe? How did these conditions influence the formation of the first galaxies? As we delve deeper into these questions, it becomes clear that fossil waves are not just remnants of the past, but a key that opens the door to understanding cosmic evolution. The importance of fossil waves lies in that they allow us to test theories about the origin of the universe. For example, the theory of inflation, which suggests that the universe expanded at an incredibly rapid rate just after the Big Bang, finds support in the information provided by these waves. Without fossil waves, many of these concepts would remain mere conjectures. Moreover, fossil waves act as a cosmic canvas on which the first structures of the universe have been drawn. Through their study, scientists can observe patterns that reveal the distribution of matter in the universe. Imagine looking at an old photo of a landscape. Even if it is blurry, you can still distinguish the outlines of mountains and valleys. In this way, fossil waves allow us to glimpse the topography of the early universe. A fascinating aspect is how these waves have been influenced by dark matter and dark energy, two mysterious components that make up most of the universe. Fossil waves help us understand how these invisible entities have shaped the structure of the cosmos, giving us clues about their nature and behavior. Isn't it intriguing to think that what we cannot see can have such a profound impact on what we can? Fossil waves also lead us to reflect on the connection between the micro and macro universe. As we explore the small fluctuations in cosmic background radiation, we can see how those small differences in temperature and density lead to the formation of large structures such as galaxies and clusters of galaxies. Every small change has the potential to trigger a series of events that culminate in what we observe today. It is astonishing to think that by studying these waves, we are not only learning about the past of the universe, but also unraveling the story of our own existence. The very particles that once were part of that primitive universe are the ones that now compose everything we know, from the bright stars in the sky to the air we breathe. Fossil waves also play a crucial role in modern cosmology. They provide data that allow scientists to refine their models and theories about the universe. Each new discovery related to these waves is like a new chapter in our understanding of the cosmos. Through them, we can establish connections between different areas of science, from physics to astronomy, enriching our overall knowledge. However, the study of fossil waves is not without challenges. As scientists delve deeper into their analysis, new questions arise that require answers. What other secrets does the universe hold that we have yet to discover? The quest for these answers is an exciting and ongoing journey that drives us to continue exploring. In summary, fossil waves are a window into the initial moments of the universe, an invaluable tool that helps us understand our cosmic history. As we continue to unravel their mysteries, each finding brings us a little closer to answering fundamental questions about the origin and evolution of the universe. In this sea of uncertainties, fossil waves emerge as beacons of knowledge, illuminating the path toward a future in which we can better understand our place in the vast cosmos. Fossil waves, those traces of the primitive universe, are not only fascinating in their nature, but also tell us a story that has been hidden for billions of years. But how can we uncover these signals from the past? The answer lies in a set of tools and techniques that allow us to listen to the echo of those initial moments. Imagine we are in a vast ocean where each wave that breaks on the shore is an echo of the Big Bang. In this way, scientists have developed ingenious methods to capture those cosmic waves. An essential aspect of detecting fossil waves is the use of radio telescopes. How do they work? Think of a satellite dish, like the ones used for watching television, but instead of picking up entertainment signals, these antennas are tuned to receive the background radiation from the cosmos. Every little flash of light they manage to capture is a fragment of the universe's history. You could say they are like detectives searching for clues in the night sky. Another crucial technique is the observation of light polarization. Can you imagine that light can dance in different ways? Polarization is like a cosmic choreography that reveals information about the conditions of the early universe. When cosmic background radiation is polarized, it gives us clues about the events that occurred at critical moments after the Big Bang. It's as if the light is trying to tell us a secret, and we have to learn to decipher its dance. Moreover, satellites play a fundamental role in this search. Mission after mission, these space observatories are launched into space, equipped with instruments that can measure the temperature and distribution of cosmic radiation in the universe. One of the most well-known is the Planck satellite, which has provided detailed maps of these waves. Imagine a camera in space capturing images of a universe that is millions of light years away. Each photo is a window to the past. The spectroscope technique also adds to our tools. This device breaks down light into its different colors, revealing information about the composition and temperature of the universe. Just like a prism that separates white light into a rainbow, the spectroscope allows us to see the hidden details of cosmic background radiation. Isn't it amazing to think that through colors we can understand the history of the cosmos? But what about experiments on Earth? Scientists do not just look up at the sky. They use particle accelerators to recreate conditions similar to those of the Big Bang. By colliding particles at extremely high speeds, they can observe how they behave and what new phenomena emerge. This is like having a miniature time machine where they can investigate the behavior of matter at moments we could never capture in space. Gravitational waves also come into play. Did you know they can be a way to detect these fossil waves? When large objects in the universe, such as black holes or neutron stars, move, they generate waves in space-time. These tremors can give us clues about the structure of the early universe and how it relates to fossil waves. It's like listening to the music of the universe, where each note reveals a fragment of our history. It is essential to mention that international collaboration is key in this field. Scientists from around the world come together to share data and discoveries. Imagine a group of musicians from different countries coming together to create a symphony. By combining their efforts, they achieve a deeper understanding of the cosmos. Each new finding is like a note that adds to the melody of knowledge. Technology has also advanced remarkably, from ultra-sensitive cameras to artificial intelligence algorithms that help analyze large volumes of data. Each innovation brings us closer to unraveling the mysteries of the universe. It's like having a superpower that allows us to see beyond what our eyes can capture. As we advance in the detection of fossil waves, intriguing questions also arise. What other surprises does the universe hold for us? Each new discovery can open the door to new theories and understandings, challenging what we thought we knew. It is an endless journey, where each answer generates more questions. Fossil waves not only help us understand the history of the universe, but also show us the nature of our own place in it. By studying these waves, we are exploring the roots of everything we know. Imagining how it all began is an exercise that connects us with the essence of our existence. So the next time you look up at the starry sky, remember that behind every bright point lies a story of fossil waves that speaks to us of the past. It connects us to a time when the universe was young and chaotic, full of energy and potential. The search for these waves is, in itself, a quest for knowledge, a human desire to understand our origin and destiny. In summary, the techniques for detecting fossil waves are a testament to human ingenuity. With each method and each discovery, we get a little closer to unraveling the secrets of the cosmos. The history is written in the waves that reach us, and we, as explorers of the universe, are here to read it. Quantum physics, a fascinating area of science, has much to say about fossil waves and their relationship with the universe. How can something so small influence something as vast as the formation of the cosmos? To understand this, it is important to first break down some key concepts. Quantum physics deals with the tiniest particles we know, those that are the building blocks of the universe. But how is this connected to fossil waves? The answer takes us to the first fractions of a second of the universe. At the moment of the Big Bang, everything we know was concentrated in a single point, a singularity that exploded in an unimaginable expansion. At that moment, the quantum nature of matter and energy became crucial. Quantum fluctuations, which are small variations in energy, began to arise in this extremely hot and dense environment. Can you imagine tiny bubbles of energy appearing and disappearing in a sea of chaos? This is how the first variations in the density of the universe were formed. These quantum fluctuations are not just curiosities. They are the seeds of what would eventually become galaxies, stars, and planets. In other words, the fossil waves we detect today are echoes of those small variations that occurred in the primordial universe. But why are they so important? Because they provide us with invaluable information about the structure of the cosmos. Each fossil wave is like a message from the past, telling us about the conditions that existed when the universe was still young. Fossil waves, in their essence, are disturbances in space-time, like ripples in a pond when you throw a stone. These waves formed due to energy fluctuations in the early universe, and their study helps us understand how the cosmos has developed. But here arises another intriguing question. What role do these waves play in the evolution of the universe? The answer may surprise you. Fossil waves are intimately connected with how matter and energy are distributed in space. Quantum physics offers a framework for understanding how these waves can influence the arrangement of galaxies and galaxy clusters. Through a process known as gravitational collapse, The small variations in the density of the primordial universe were amplified over time, forming larger structures. Imagine these waves as a set of musical notes. Some notes are amplified and resonate more than others, creating the beautiful symphony of the cosmos. Furthermore, quantum physics also helps us understand the nature of dark matter, which is believed to make up a large part of the universe. Dark matter interacts with light and normal matter in subtle but crucial ways. Without this interaction, the fossil waves we observe today would not have the same shape or meaning. It's as if dark matter were a conductor, guiding the interpretation of the waves on the vast stage of the universe. But it's not just dark matter that plays a relevant role. Dark energy, which drives the accelerated expansion of the universe, is also intertwined with fossil waves in surprising ways. As the universe expands, fossil waves also stretch, changing their characteristics over time. This stretching is an effect that quantum physics helps to explain, showing how the properties of space-time can affect the waves traveling through it. Space missions like Planck and WMAP have been fundamental in this context. These satellites have collected data on cosmic microwave background radiation and fossil waves, breaking down the information into patterns that scientists can analyze. But what do these data really tell us? They offer us a glimpse into the history of the universe, revealing details about its composition and evolution that were once unimaginable. As we continue to explore these interactions, we find that quantum physics is not limited to describing phenomena on a small scale. It also provides a theoretical basis for understanding how the forces of the universe intertwine, affecting both visible and invisible matter. This leads us to reflect on humanity's place in the cosmos and how our understanding of fossil waves brings us a little closer to unraveling the mysteries of the universe. The implications of all this are profound. Every discovery about fossil waves is another piece of the cosmic puzzle. It forces us to rethink our understanding of time, space, and matter. Fossil waves, along with quantum physics, show us that the universe is a much more complex place than we ever imagined. So the next time you think about fossil waves, remember that they are more than just simple echoes of the past. They are a testament to the extraordinary journey of the universe, to the small fluctuations that shaped everything we know. And while there are still many unanswered questions, each advance in our understanding of quantum physics and fossil waves brings us one step closer to discovering the truth about the cosmos. Have you ever wondered how the structures we see in the universe today were formed? The answer to that question goes back to the early moments after the Big Bang. In those moments, the universe was a chaotic place, full of energy and particles. As it began to expand and cool, small fluctuations in the density of matter started to appear. But what does this really mean? The fluctuations in density are like small waves in a sea. Imagine the universe as a vast ocean. In this ocean, some areas are denser than others. These variations in density are crucial because they are the first step towards the formation of the structures we know today. Galaxies, stars, and planets. Without those small differences, the universe would be a rather dull place, filled with uniform matter and no interesting shapes. So how do these fluctuations originate? During the time of the Big Bang, the universe was not only expanding but also dominated by quantum physics. This branch of science tells us that at very small scales, particles do not behave predictably. Instead, they are full of probabilities. So in this chaotic environment, quantum fluctuations began to play a fundamental role. It's as if, in a turbulent sea, some waves were taller than others, creating small islands of density that, over time, would become galaxies. But why are these fluctuations so important? Imagine you are at a party and notice that some groups of people are closer to each other. Over time, those groups can become the center of attention at the party, while others dissipate. In the universe, those areas of higher density began to attract more matter around them, forming more complex structures. As the universe continued to expand and cool, these small fluctuations became what we now know as the large structures of the cosmos. Galaxies, clusters of galaxies, and even superclusters began to emerge from these small variations. Without these fluctuations, which are essentially the footprints left by the early universe, our galaxies would never have reached their current form. The relationship between density fluctuations and structure formation is a bit like a game of dominoes. At first, a small push on one of the pieces can cause an entire row to fall. In the universe, the small differences in density served as the initial push that led to the formation of massive structures. Thus, the universe wove a tapestry of interconnected galaxies. One fascinating aspect of these fluctuations is that they are not homogeneous. Some areas of the universe contain more matter, while others have less. This pattern of distribution is fundamental to understanding how galaxies are organized and how they cluster together. Isn't it amazing to think that those small variations may have given rise to everything we see in the sky? Moreover, these fluctuations not only affect visible matter, but also dark matter. Although we cannot see dark matter, we know it is there because its gravity affects the movement of galaxies. In a sense, we could say that dark matter plays a supporting role in the universe's masterpiece, helping to shape the structures that emerge from density fluctuations. But what about the big questions? How do these fluctuations influence our place in the cosmos? The answer is that these variations are the reason we are here. Without them, Earth, our home, would not exist. Every star we see in the sky and every planet orbiting around it is the result of those small differences in density that occurred in the early moments of the universe. Thinking about density fluctuations is not just an academic exercise, it is a way to understand our place in the vast universe. It invites us to reflect on how each of us, like the galaxies, has a unique role in the grand scheme of things. Just as small ripples in water can create large waves, our own actions and decisions can have repercussions that extend far beyond what we can imagine. In summary, the fluctuations in the density of the early universe are like the seeds of a cosmic garden. From those small variations, galaxies, stars, and eventually life itself sprouted. The story of our universe is a tale of chaos and order, of small differences that led to astonishing complexity. As we continue to explore the cosmos, those fluctuations remind us that, although we are small compared to the vastness of the universe, each of us has an important role to play in this vast and wonderful story. When we observe the vast universe, it is easy to feel overwhelmed by its immensity and complexity. But how are the galaxies and clusters of galaxies that we see today actually organized? The answer to this enigma lies in the fossil waves. Those traces of the past that tell us stories about the first moments after the Big Bang. Through them, we can glimpse not only how the universe was formed, but also the role they play in its current structure. Fossil waves are like the echo of a distant melody, resonating through time and space. In this case, we are talking about the fluctuations in density that occurred in the early universe. Imagine a calm ocean, where suddenly small waves are created. These waves are the fluctuations that would eventually give rise to the galaxies and structures we see in the cosmos. Without these waves, the universe would be a very different place, likely devoid of the beauty and diversity we observe today. To better understand their influence, let's think about how galaxies are distributed in space, just like at a party where people group together in different corners. Galaxies cluster into groups and superclusters. But what determines where they group? Fossil waves provide us with clues about this. The fluctuations in the density of the early universe created regions where matter accumulated more densely and others where there was less. Over time, these small differences were amplified, leading to the formation of the structures we observe today. The relationship between fossil waves and the distribution of galaxies is fundamental for cosmologists. When we study these waves, we can map the history of matter in the universe. It's like analyzing an ancient map that reveals how territories have changed over time. In this case, fossil waves act as our map, showing us how matter was organized and evolved in the early stages of the universe. Now, when we look at the universe, we notice that not all areas are equally populated. Some regions have a high concentration of galaxies, while others appear empty. Why does this happen? Fossil waves, being the result of variations in density, are responsible for this uneven distribution. Areas where density was higher became the birthplaces of galaxies, while in areas of lower density, galaxy formation was less likely. Moreover, fossil waves not only inform us about the distribution of galaxies, but also speak to their evolution by studying how they have changed over time. Scientists can gain insights into the history of the universe. For example, if we observe a region of space containing a large number of galaxies, we can infer that that area had a higher concentration of matter in the past, which facilitated the formation of those galaxies. But what about the galaxies that are farther away from us? Fossil waves also help us understand their movement. As the universe expands, galaxies move away from each other. This phenomenon is known as the expansion of the universe and is a direct result of the initial properties set by the fossil waves. If the universe had not had those fluctuations, the expansion might have been different, affecting how galaxies are distributed in space. Imagine you have a balloon and draw points on its surface. As you inflate the balloon, those points move away from each other. This is a simple model of how the expansion of the universe works. Fossil waves are like those drawn points. They show us how things started and allow us to understand their evolution over time. The study of fossil waves has also led to surprising discoveries about dark matter and dark energy, two components that play a crucial role in the structure of the universe. Dark matter, which we cannot see directly, interacts with visible matter and affects how galaxies cluster. Fossil waves give us clues about the amount of dark matter present in the universe and its influence on the formation of structures. On the other hand, dark energy, which seems to be driving the acceleration of the universe's expansion, is also related to fossil waves. By studying the fluctuations and how galaxies are distributed, we can gain insights into the nature of dark energy and how it affects the evolution of the cosmos. It is fascinating to think that fossil waves are not just relics of the past, but powerful tools for understanding the present and future of the universe. As we delve deeper into the research of these waves, we discover that they are the key to unraveling many of the mysteries that still remain to be solved. The large-scale structure of the universe, from galaxy clusters to vast empty regions, is intrinsically linked to fossil waves. These waves offer us a window into the past, allowing us to observe how the structures that now make up our universe were formed. Thus, every galaxy we see in the sky is a reminder of the waves that once vibrated in the vast cosmic ocean. Therefore, when contemplating the starry sky, we do not just see distant lights, but also echoes of a primordial time. Fossil waves are the thread that connects us to those initial moments, showing us how matter was organized and how it has evolved into the universe we know today. In every galaxy, in every cluster, resides the history of our cosmos, told through the waves that have survived the vastness of time. The theory of cosmic inflation is like a fascinating story that invites us to discover how everything we know began. What happened in the universe in its earliest moments? The answer lies in the idea that just after the Big Bang, the universe underwent an incredibly rapid expansion, almost like a balloon inflating at a surprising speed. But why is this expansion so important for the cosmic background radiation? When we think of the universe, we often imagine it as a vast space filled with stars and galaxies. However, in its early moments, everything was much simpler, a kind of hot soup of particles. At the same time, the cosmic background radiation, which are echoes of that expansion, began to form. These waves are like the ripples created when we throw a stone into a pond, but in this case, the pond is the very fabric of space-time. Cosmic inflation helps us understand how those cosmic background waves were created. During that rapid expansion, small fluctuations in the density of the universe began to grow and become the seeds of the structures we see today. Have you ever wondered how it is possible that galaxies are distributed the way they are? The answer can be found in these small variations that were amplified thanks to inflation. As the universe expanded, the cosmic background radiation stretched and cooled. Imagine stretching an elastic band. As you stretch it, the band becomes thinner. Similarly, the waves that had been created in that first moment of the universe expanded and transformed. This process is crucial because it gives us clues about how the large-scale structures we observe today were formed. Cosmic inflation not only explains the origin of the cosmic background radiation, but also suggests that the universe is much larger than we can see. Have you often wondered what lies beyond what we can observe with our telescopes? The theory of inflation suggests that there could be regions of the universe that we will never see, simply because they are beyond our observable horizon. Now, it is essential to understand that these cosmic background waves are not just scientific curiosities. They are messages that have come to us from the past, like letters from the universe that help us unravel its history. Through them, we can discover not only how the universe was formed, but also how it has evolved over billions of years. The connection between cosmic inflation and cosmic background radiation is a thread that weaves the story of the cosmos. When scientists observe the cosmic microwave background radiation, they are looking deep into the past, almost as if they could hear the murmur of the universe's earliest moments. Isn't it amazing to think that every time we look at the stars, we are in a way looking back in time? The theory of inflation also raises intriguing questions about the uniformity of the universe. Why is it so homogeneous on large scales? The answer may be linked to the rapid expansion, which would have allowed regions of space to mix and balance before galaxies began to form. This means that the universe we see today is the result of a very dynamic and complex process. Moreover, cosmic inflation leads us to reflect on the future of the universe. Will it continue to expand forever? The answer may be related to the properties of the cosmic background radiation. By studying how these waves are distributed and how they have changed over time, scientists can make conjectures about the future evolution of the cosmos. The relationship between inflation and cosmic background radiation is not only fascinating from a scientific perspective, but also invites us to explore the mystery of existence itself. What does it really mean for us as human beings to understand that we are part of a constantly expanding and changing universe? As we delve deeper into the connection between cosmic inflation and cosmic background radiation, we face the possibility that the universe is stranger and more beautiful than we ever imagined. Each discovery in this field opens new doors to even deeper questions. Are we alone in this vast cosmos, or are there other worlds we have yet to discover? Cosmic inflation and cosmic background radiation teach us that the universe is not just an empty space, but a place full of history and mysterious dynamics. At the end of the day, every time we look at the starry sky, we are not only contemplating the past, but also the depth of the questions that remain to be answered. So the next time you think about the cosmos, remember that every star and every galaxy is part of a much larger story, a story that began with inflation and cosmic background radiation and continues to unfold before our eyes. There are no limits to what we can learn, and each new revelation about our existence only adds more wonder to the marvel of the universe. Have you ever looked up at the starry sky and wondered what the universe looked like right after the Big Bang? The fossil waves are like the fingerprints of the primitive universe, and understanding their evolution offers us a fascinating glimpse into how our cosmos has changed over billions of years. When we talk about fossil waves, we refer to those small ripples in the cosmic microwave background radiation, which are silent witnesses to the history of the universe. But how have these waves evolved from their earliest moments to the present day? To understand this, let's think about a serene lake. When you throw a stone into the water, waves are generated that propagate across the surface. Fossil waves are somewhat like those waves, but instead of water, they exist in the vast expanse of the universe. When the universe was a hot and dense place, these waves formed, and as the universe expanded and cooled, those waves lost energy and changed shape. The question is, what happened to them on their journey through time? Over the centuries, fossil waves did not remain static. As the universe expanded, these ripples stretched and changed. Imagine stretching a rubber band. As you do so, the original shape modifies and becomes something different. Thus, the fossil waves generated in the early moments of the universe have transformed, but their essence remains, telling us about the conditions in which they were formed. One of the most intriguing questions is, how do we know that these fossil waves have changed? Just like an archaeologist studying layers of soil to understand the past, scientists analyze the cosmic microwave background radiation to trace the evolution of these waves. This means that by observing the small variations in the temperature of this radiation, we can infer what the waves were like in their original state. Each small fluctuation is like an echo from the past, revealing secrets about the history of the universe. However, it's not all that simple. Along their evolutionary path, fossil waves have also been influenced by other factors. One of them is dark matter, which, although we cannot see it directly, has a significant impact on how the waves behave. Have you ever felt something pushing you without being able to see it? That's somewhat what happens with dark matter. It influences the structure of the universe and in turn affects the fossil waves. But how exactly does it do this? As the universe continued to expand, the influence of dark matter helped shape galaxies and clusters of galaxies. Imagine a spider web. Each thread is a galaxy, and dark matter is the point where they meet. The fossil waves, by interacting with this network of dark matter, began to create the structures we see today. But the story doesn't end here. Dark energy, that enigmatic component that seems to be accelerating the expansion of the universe, also plays a crucial role. You might wonder, how is this related to fossil waves? Dark energy acts like a motor that pushes the universe to keep expanding, and this expansion affects how fossil waves manifest in our time. It's as if an invisible wind were sculpting the shape of a landscape, altering the marks that time has left. It's fascinating to think that despite the changes and transformations, fossil waves remain a bridge between the past and the present. They tell us how the universe was formed, how it has evolved, and how, over billions of years, they have left their mark on the cosmic radiation. But what does the future hold for us in this quest for knowledge? As scientists continue to explore and improve technologies to study fossil waves, we may discover new secrets that we have yet to imagine. The evolution of fossil waves is not only a journey through time, but also an invitation to keep questioning and discovering. What else will these waves tell us about the design of the universe, about its origin and its ultimate fate? Finally, reflecting on all this, it is clear that fossil waves are much more than simple ripples in space. They are an epic tale of how a constantly changing universe has come to be what it is today. As we continue to delve into their evolution, we are, in a way, exploring our own history and what it means to be part of this vast cosmos. The next time you look at the stars, remember that although fossil waves have changed, their story remains alive in every corner of the universe. Have you ever wondered how the things we cannot see can affect everything around us? In the vast universe, there is an intriguing entity that plays a fundamental role in how galaxies, stars, and ultimately life itself develop: dark matter. But what exactly is dark matter, and why is it so crucial for understanding cosmic microwave background radiation? Dark matter is a type of matter that neither emits, absorbs, nor reflects light, making it completely invisible to our eyes and traditional telescopes. However, despite not being able to see it, we know it is there due to its gravitational influence. It's like having a friend who is always pushing you forward, but you can't see or feel them directly. This invisible friend has been essential in the formation of structures in the universe. Now, how does dark matter connect with cosmic microwave background radiation? To understand this, let's imagine the early universe shortly after the Big Bang. At that moment, everything was chaos and energy. Amidst this turmoil, cosmic microwave background radiation emerged as echoes of that initial explosion. These waves, which are variations in the density of the universe, tell us a story about how the first structures formed. This is where dark matter comes into play. Dark matter acts as an invisible scaffolding that helps shape the universe. Without it, galaxies would not have been able to cluster as they do. Cosmic microwave background radiation shows us how dark matter influenced the distribution of normal matter, the kind we can see. So, when we study these waves, we are also, in a way, observing the effect of dark matter on the evolution of the cosmos. An intriguing question is, how do we know dark matter exists if we cannot see it? Scientists have detected its presence through observations of the rotation of galaxies. Imagine you are spinning on a carousel. If there is more weight on one side, the carousel will spin differently. Similarly, galaxies rotate in a way that suggests there is more mass present than we can see. This hidden mass is dark matter. The relationship between cosmic microwave background radiation and dark matter doesn't stop there. Throughout the history of the universe, dark matter has guided the formation of galaxies and galaxy clusters. The fluctuations in density that we observe in cosmic microwave background radiation are largely the result of the gravitational influence of dark matter. Without it, the small density variations that became large and complex structures might have vanished in that sea of energy of the early universe. It's fascinating to think that cosmic microwave background radiation offers us a map of the early universe, where dark matter acted as a silent architect. But what is the role of dark matter in the expansion of the universe? This is where the story becomes even more intriguing. As the universe expands, dark matter continues to exert its influence, affecting the rate at which structures form and evolve. So what about dark matter and dark energy? While dark matter acts as a glue that holds galaxies together, dark energy seems to be pushing the universe to expand faster and faster. It's as if you have a balloon that, in addition to inflating, is also stretching. Dark matter and dark energy are two sides of the same coin, and together they help us understand the dynamics of the cosmos. As we continue to investigate cosmic microwave background radiation, scientists seek to better understand the nature of dark matter. There are theories suggesting it could be composed of yet-to-be-discovered subatomic particles. Imagine there is an entire world of things we simply haven't found, like a cave full of hidden treasures. Each new finding in dark matter research could open new doors to our understanding of the universe. The search for dark matter and its relationship with cosmic microwave background radiation also raises questions about how the first stars and galaxies formed. While normal matter forms the stars we see in the sky, dark matter has been the backdrop that has allowed those stars to cluster and evolve. Without dark matter, the universe as we know it could be a very different place. It's astonishing to think that despite dark matter constituting approximately 85% of the universe's mass, we still do not fully understand what it is. Each new discovery about cosmic microwave background radiation and dark matter is like another brick in the construction of our knowledge of the cosmos. Finally, as we reflect on dark matter and its influence on cosmic microwave background radiation, we realize that we are only at the beginning of a fascinating journey. Science is constantly evolving and redefining what we know about the universe. Each discovery brings us one step closer to unraveling the mysteries of the cosmos. So, what else will cosmic microwave background radiation reveal to us in the future? The answer is waiting to be discovered in a universe full of surprises. Dark energy is one of the greatest mysteries of the cosmos. What exactly is it? To understand it, let's think about how the universe behaves. Imagine the universe is like a balloon. When you inflate the balloon, it expands, and the marks you drew on its surface move away from each other. In the universe, that expansion also occurs, but there's something that makes it even more intriguing. The expansion is accelerating. This is where dark energy comes in. Dark energy represents about 73% of the total energy and matter in the universe. It seems to be pushing the universe into a constant and accelerated expansion. However, despite its great influence, we cannot see or measure it directly. In a sense, it's like the air in the balloon. We don't see it, but we know it's there because the balloon expands. Astronomers have reached this conclusion from observations of distant supernovae. When these stellar explosions are observed, scientists noticed that some of them appear dimmer than they should. This means they were farther away than previously thought, suggesting that the universe is expanding at a faster rate. But what causes this acceleration? The answer is still unclear, and that is what makes it so fascinating. The relationship of dark energy with cosmic microwave background radiation is equally intriguing. The cosmic microwave background, which is the afterglow of the Big Bang, provides us with a snapshot of the universe in its infancy. By studying this radiation, scientists can glean clues about the total composition of the universe, including the amount of dark energy. It's as if this radiation is an ancient map guiding us through time and space. Now imagine you are in a maze and you have a map showing where the exits are. The cosmic microwave background is that map, while dark energy is the complicated terrain you must navigate. Without understanding dark energy, it's difficult to interpret the map correctly. How can we get an idea of how this mysterious force works? One way to approach it is to think about how dark energy affects the large-scale structure of the universe. If dark energy were absent, galaxies and galaxy clusters would behave differently. Gravity, which is attractive, would play a more significant role in the formation and evolution of cosmic structures. But dark energy acts as a repulsive force, dominating the expansion on much larger scales. Scientists are working hard to better understand dark energy. There are theories suggesting it could be a form of vacuum energy, a kind of pressure that exists even in empty space. Others propose that it could be a modification of gravity on a large scale. Each theory offers a new angle to try to unravel this cosmic enigma. Dark energy also raises philosophical questions. If most of the universe is composed of something we cannot see or fully understand, what does that mean for our understanding of the cosmos? We face the possibility that there is much more in the universe than we can perceive. This idea can be unsettling, but also exciting. It invites us to explore and discover. Experiments and observations continue. Missions like the Hubble Space Telescope and the Dark Energy Survey satellite are specifically designed to study the expansion of the universe and the nature of dark energy. With each new image and each set of data, we get a little closer to unveiling this mystery. But will it be enough to answer the question of what dark energy really is? Some scientists believe that by understanding how cosmic microwave background radiation interacts with dark energy, we could have a clearer picture of the history of the universe. It's like having two pieces of a puzzle. Although we don't know how they fit together, each new piece we find can bring us closer to the complete picture. The search for answers about dark energy also reflects human curiosity. Since time immemorial, we have looked to the sky, wondering about our place in the vast universe. Dark energy, with its elusiveness and influence, reminds us that there is still much to discover. As we move forward in this quest, we face questions that challenge not only our scientific capabilities, but also our imagination and understanding of the cosmos. In summary, dark energy is an essential component of the universe that, although invisible, plays a crucial role in its evolution. The cosmic microwave background provides us with the key to begin understanding this mysterious phenomenon. Research continues, and each discovery brings us one step closer to unveiling one of the great secrets of the universe. The fascination with the unknown is what drives scientists and humanity as a whole. And dark energy is just one of the many mysteries awaiting us in the vast expanse of the cosmos. What role have space missions like Planck and WMAP played in our understanding of the universe? These probes have acted like detectives in a vast cosmic scene, searching for clues about the nature of primordial waves. Their mission was to unveil the secrets hidden in the cosmic microwave background radiation, that echo of the Big Bang that still resonates throughout the universe. But how did they do it? The WMAP mission, launched in 2001, was the first major step in this quest. Imagine a telescope that not only observes but also listens to the murmur of the universe. WMAP measured the temperature of the cosmic microwave background with astonishing precision, revealing patterns that spoke to us about the history of the cosmos. Did you know that these patterns are like the fingerprints of the universe? Every small change in temperature tells us something about matter, energy, and the structure of the universe. But why is the cosmic microwave background radiation so important? This radiation is like a photograph of the universe when it was just 300,000 years old. WMAP captured that image and allowed us to understand how the first galaxies and stars formed. With each piece of data it collected, the mystery of how we transitioned from a hot soup of particles to a cosmos filled with structures became a little clearer. Then came the Planck mission, launched in 2009. This probe took the precision of measurements to a new level. With its ability to map the cosmic microwave background in high definition, Planck became the artist that painted a clearer portrait of the early universe. Can you imagine having a camera that can see through time? That's what Planck did, revealing details that were previously invisible. One of the most exciting revelations from Planck was the measurement of anisotropy in the cosmic microwave background. These small variations in temperature are like wrinkles on a sheet of paper. They show us that the universe is not a perfectly uniform place. What does this mean? That since its beginnings, the universe has been filled with chaos and disorder, which ultimately allowed galaxies and the structures we see today to form. By analyzing the data from Planck, scientists were also able to determine the age of the universe with unprecedented accuracy. Have you ever wanted to know how old something is? With the information collected, it is estimated that the universe is approximately 13.8 billion years old. With each passing day, we continue to get closer to understanding our place in this vast cosmic stage. Moreover, these missions have allowed scientists to explore the composition of the universe. Did you know that a large part of what makes up the cosmos is dark matter and dark energy, things we cannot see directly? The data from Planck and WMAP have helped confirm the presence of these mysterious components, revealing that we are surrounded by a universe that is largely invisible. A fascinating aspect is how these missions have impacted our theories about the formation of the universe. The information obtained has led to a better understanding of cosmic inflation, a theory suggesting that the universe expanded rapidly in its early moments. Can you imagine a balloon inflating faster than you can follow it? That's what happened in the early universe, and the primordial waves are the traces of that expansion. Comparing the data from WMAP and Planck has been crucial for refining our theories about the cosmos. As scientists analyze the differences and similarities between the results of these two missions, a new field of research opens up. What new questions will arise from these comparisons? Human curiosity knows no bounds, and every answer seems to generate more questions. Additionally, the missions have not only focused on the cosmic microwave background, but have also provided data on the distribution of galaxies in the universe. By examining how galaxies cluster, scientists have been able to map the large-scale structure of the cosmos. Isn't it incredible to think that by looking at the sky, we are witnessing a story of how everything we know has formed? The international collaboration behind these missions is also worth mentioning. Scientists from around the world have worked together to develop technologies and strategies that have made the collection of cosmic data possible. This collective effort highlights how the pursuit of knowledge transcends borders. What if we are all united by this shared curiosity about the universe, regardless of where we come from? As we move forward, the lessons learned from these missions continue to influence the design of future explorations. Technology has evolved, and so have our questions. What new discoveries await us on the horizon? The exploration of the cosmos is an endless journey, full of surprises and discoveries that challenge our understanding. In conclusion, the Planck and WMAP missions have been fundamental in unraveling the secrets of the early universe. Through their observations, we have gained a clearer view of the cosmic microwave background and therefore of the history of the cosmos. Each piece of data collected is a brick in the construction of our knowledge, and each discovery brings us a little closer to understanding the vast and mysterious universe in which we live. What revelations will the future bring us? The adventure is just beginning. Fossil waves have revolutionized our understanding of the universe, but what are the implications of these discoveries for modern cosmology? To understand this, it is essential to delve into how these waves have changed our view of the cosmos, from their origins to their current evolution. First, let's imagine the universe as a vast ocean of possibilities. In this ocean, fossil waves are like the waves that carry with them the history of their formation. These waves, which emerge shortly after the Big Bang, act as an echo of the past, telling us what the universe was like in its early moments. But what specific information do they provide us? Fossil waves offer us a window into the structure of the universe. Through them, scientists can map the distribution of matter in the cosmos. It's as if we have an ancient map that reveals how a continent was shaped over time. Without fossil waves, many of the current theories about the formation of galaxies and galaxy clusters would lack foundation. Isn't it amazing to think that these waves allow us to visualize a universe we have never seen directly? Moreover, fossil waves are crucial for validating or challenging cosmological theories. For example, the theory of inflation, which suggests that the universe underwent exponential expansion in its early moments, has been supported by data obtained from fossil waves. But what would happen if this data did not align with what the theory suggests? The answer to this question could lead us to rethink fundamental concepts about the universe and its history. Another fascinating aspect is how fossil waves help reveal the nature of dark matter. This mysterious substance, which does not emit light and is invisible, represents the majority of the universe's mass. Fossil waves act as a guide, indicating how dark matter has influenced the formation of large-scale structures. Without this guide, tracking dark matter would be like trying to find a lighthouse in the fog. Similarly, fossil waves play a crucial role in understanding dark energy. This phenomenon, which is causing the universe to expand at an accelerated rate, raises intriguing questions about the ultimate fate of the cosmos. Could fossil waves, by providing information about the dynamics of the universe, help us better understand the nature of dark energy? The answer could change not only our view of the universe, but also our understanding of physics itself. The discovery of cosmic microwave background radiation, which is essentially the manifestation of fossil waves, was a milestone that opened a new path in cosmology. This discovery, made by Arno Penzias and Robert Wilson in 1965, not only confirmed the Big Bang theory, but also laid the groundwork for a new field of study. How has this finding influenced the way scientists investigate the cosmos today? Space missions such as Planck and WMAP have been fundamental in collecting data on fossil waves. Through these missions, we have been able to obtain detailed images of the cosmic background, allowing scientists to meticulously analyze temperature and density patterns. What secrets have these images revealed, and how have they contributed to our understanding of the evolution of the universe? But it's not just about data and numbers. Fossil waves also lead us to reflect on our place in the cosmos. As we unravel their meaning, we face philosophical questions about the origin of everything. What does it really mean to understand the universe? Fossil waves invite us to consider not only the past of the cosmos, but also our future within it. Through the analysis of fossil waves, we have been able to construct a story of the universe that spans from its birth to its current expansion. This narrative offers us the opportunity to glimpse the future of the cosmos. Could we be on the verge of a radical change in our understanding of the universe in the coming decades as we advance in our research on these waves? Finally, when thinking about the implications of fossil waves for modern cosmology, it is hard not to feel excited. We find ourselves at a moment when our curiosity and technology are driving a new renaissance in the exploration of the universe. Fossil waves are not just a relic of the past. They are the key to opening new doors and unraveling the mysteries that still await discovery. In the end, fossil waves remind us that although we have made progress in understanding the cosmos, there is still much more to explore. Each discovery brings us a little closer to unveiling the history of the universe, a story as old as time itself that continues to evolve before our eyes. Fossil waves are not just an echo of the past. They also serve as a fascinating bridge between cosmology and astrophysics. How is it possible that these waves, which formed in the early moments of the universe, are connected to such diverse phenomena as star formation or galaxy dynamics? To understand this relationship, it is essential to explore how fossil waves provide clues about the structure and evolution of the cosmos. One way to think about this is to imagine a calm lake. When you throw a stone, waves are produced that propagate through the water. These waves are not just a simple movement, they reveal information about the object that caused the disturbance. Similarly, fossil waves are the result of events that occurred in the primitive universe and tell us stories about its origin and development. One of the most intriguing aspects of fossil waves is how they influence the distribution of matter in the universe. Did you know that the way galaxies group and separate is related to these waves? Through cosmic microwave background radiation, we can observe the traces of fluctuations in the density of the early universe. These fluctuations are like variations on the surface of the lake, indicating where there is more matter and where there is less. Fossil waves act as a map of the universe, and as we delve into this map, we discover surprising connections. Why do some galaxies seem to be closer to each other, while others are so distant? Fossil waves help us understand that gravity, driven by dark matter, plays a crucial role in the formation of these structures. This leads us to a fascinating question. How can we be sure that dark matter really exists, and how does it affect fossil waves? The answer lies in the way dark matter interacts with radiation. Although we cannot see dark matter directly, its influence is undeniable. Like a magnet that attracts metallic objects without being visible, dark matter affects how fossil waves are distributed in the universe as galaxies cluster into groups. These interactions leave marks on the waves that we can study. And speaking of marks, another intriguing question is, what do fossil waves tell us about dark energy? This mysterious force seems to be accelerating the expansion of the universe, and its relationship with fossil waves is an area of active research. By analyzing these waves, scientists can gain insights into how dark energy is shaping the fate of the cosmos. Imagine that fossil waves are like a love letter that the universe has left us. That letter not only speaks of its history but also gives us clues about its future. As we explore these connections further, we begin to glimpse an interconnected cosmos where every element has a role to play. Astrophysics, for its part, also benefits from this relationship with fossil waves. The waves not only inform us about the past of the universe, but they can also unveil secrets about star formation and the evolution of black holes. For example, by studying how galaxies are distributed, we can infer how fossil waves have influenced the formation of new stars and the death of others. A significant intersection lies in the study of neutrinos. These almost invisible particles, which are also a fundamental part of the universe, relate to fossil waves in surprising ways. By investigating how neutrinos are generated and behave, scientists can obtain a clearer picture of the conditions in the early universe, which in turn influence the formation of large-scale structures. The dialogue between cosmology and astrophysics is, in essence, a game of questions and answers. Each discovery about fossil waves raises new questions that astrophysicists seek to answer. How do different structures in the universe relate to each other? What do they teach us about the nature of gravity? These questions lead us on a continuous journey of exploration and discovery. It is fascinating to think that by studying these waves, we are not only looking back at the past, but also searching for clues about the very nature of the universe. Fossil waves show us that the cosmos is not a static place but a dynamic landscape full of interactions and connections. As we look to the future, it is clear that research on fossil waves and their relationship with astrophysics will continue to be a key field for unraveling the mysteries of the universe. The next time you look up at the starry sky, remember that each of those stars and galaxies has a story to tell. A story that begins with the fossil waves that still resonate in the vast cosmos. The understanding of the universe has been a fascinating journey, filled with discoveries that challenge our perception of reality. However, what if I told you that there are theories that call into question the conventional view of how the cosmos was formed and is evolving? Some of these alternative theories even challenge the fundamental principles we have learned about the Big Bang and cosmic background radiation. One of these intriguing theories is that of the oscillating universe. Can you imagine a universe that, instead of having a beginning and an end, expands and contracts infinitely? According to this theory, after each expansion, the universe eventually contracts again, culminating in a big crunch. This cycle could repeat eternally, suggesting that our linear understanding of time and existence might be limited. In this model, cosmic background radiation would not just be an echo of the past, but a representation of infinite cycles of creation and destruction. Another theory that challenges the conventional view is that of the static universe. This concept, although less popular today, was defended by some scientists in the past. Instead of an expanding universe, it is suggested that the cosmos could be eternal and unchanging. However, how do cosmic background radiation fit into this model? The answer is that under this theory, cosmic background radiation could be considered a secondary phenomenon rather than a key to understanding the origin of the universe. This raises fascinating questions about the nature of time and space. Now let's talk about the multiverse theory. Imagine a scenario in which our universe is just one of many, each with its own physical laws and structures. In this context, cosmic background radiation could be the result of interactions between different universes. Thus, what we observe as cosmic microwave background radiation could be a trace of the collision between our universe and another. What implications would this have for our understanding of what we consider real? String theory is another intriguing approach that seeks to explain the fundamental nature of the universe. It proposes that subatomic particles are not points but vibrating strings that can exist in multiple dimensions. While this theory offers a way to unify quantum physics and relativity, it raises the question, how does this affect cosmic background radiation? Some researchers suggest that these strings may have influenced the formation of cosmic background radiation in the early universe, leaving a trace that we can still detect today. Next, the idea of a holographic universe invites us to reconsider our perception of reality. According to this theory, all the information that makes up our universe may be contained on a two-dimensional surface, like a three-dimensional projection. Thus, cosmic background radiation could be seen as projections of information stored on this holographic surface. This suggests that what we see and experience may be just a representation of something much more complex. Scientists have also considered the possibility that cosmic background radiation is the result of interactions with yet undiscovered forms of matter. Imagine there are particles that we have not detected that could alter the way we understand cosmic microwave background radiation. This opens up a world of possibilities and raises the question, what else might be hidden in the corners of the universe waiting to be discovered? Moreover, Einstein's theory of relativity has been fundamental to our understanding of the cosmos, but some researchers are exploring variations that could completely change our perspective. What if gravity were not constant but fluctuated over time? This could have repercussions on how we interpret cosmic background radiation and its relationship with the expansion of the universe. Quantum gravity theories also offer an intriguing perspective. This area of research seeks to unify quantum physics and general relativity and could provide new answers about the origin of cosmic background radiation. If we can understand how gravity behaves at quantum scales, we might find the key to solving some of the universe's deepest mysteries. We cannot forget the possibility that additional dimensions exist that influence our perception of the cosmos. According to some theories, we might be limited to perceiving only 3 spatial dimensions and 1 temporal dimension, while in reality there could be many more. How would this impact the way we interpret cosmic background radiation and its role in the evolution of the universe? Finally, it is crucial to consider that science advances through the exploration of ideas and theories. Alternative theories, although often challenged by evidence, push us to think beyond what we know. As scientists continue to explore the cosmos, it is possible that some of these theories will find support in new discoveries, transforming our understanding of the universe forever. In this context, cosmic background radiation is not simply an echo of the past, but a gateway to a future of infinite possibilities. The quest for answers leads us to question not only how the universe began, but also what our existence within it might mean. Are we ready to accept that reality could be stranger and more complex than we ever imagined? The adventure of science continues, challenging us to explore and question as we unravel the secrets of the cosmos. Research on fossil waves is at a fascinating and crucial moment. What new frontiers could open in our understanding of the universe? Human curiosity has always driven scientists to explore the unknown. And in this case, fossil waves are an intriguing starting point. With each discovery, we get a little closer to unveiling the mysteries of the cosmos. The first step towards the future of fossil wave research is the improvement of detection technologies. As we advance in the development of more sophisticated tools, new opportunities arise to study these waves with greater precision. Imagine a telescope that can see beyond what our eyes can capture, revealing details that were previously hidden. What secrets could such an instrument unveil? A promising aspect is the exploration of the polarization of cosmic background radiation. This subtle feature could hold clues about the early moments of the universe. Polarization is like the shimmer on a water surface. It can reflect small details that would otherwise go unnoticed. What revelations will these small variations in the light coming from the depths of the cosmos bring us? Moreover, the study of gravitational waves, which are like echoes of the Big Bang, intertwines with the research of fossil waves. These waves are generated by violent events in the universe, such as the merging of black holes. By listening to these echoes, we could gain a new perspective on the formation and evolution of the universe. What stories would these echoes from the past tell us? The future may also bring the discovery of new particles that interact with dark matter. Understanding more about dark matter is crucial, as it represents a large part of the universe's content. If we could identify how these particles affect fossil waves, we would be one step closer to understanding the structure of the cosmos. What new truths would be revealed if we could see the interactions between these hidden forces and the waves reaching us from the dawn of time? Artificial intelligence is also becoming a powerful tool in fossil wave research. With its ability to analyze large volumes of data, AI can uncover patterns that humans might overlook. Could a machine help us unravel the secrets of the universe in ways we never imagined? As new theories develop, the question arises of how these theories align with fossil waves. The theory of cosmic inflation, for example, has been fundamental in modern cosmology. If new aspects of this theory are confirmed, they could redefine our understanding of how the universe was born. Are we on the verge of entering an era where we can confirm or refute theories that have been debated for decades? It is also fascinating to think about how international collaboration in fossil wave research can enhance our knowledge. With scientists from around the world joining forces, different perspectives and approaches can be combined to tackle complex questions. Could this global collaboration lead us to discoveries that will change our view of the universe? Additionally, the impact of education and scientific outreach cannot be underestimated. As more people become interested in science, research on fossil waves can receive a significant boost. How might public enthusiasm influence funding and support for new research projects? Human curiosity manifests itself in more than just the search for answers. The way we formulate questions also evolves. With each new answer, new questions arise. What questions will be asked in the future about fossil waves that we have yet to conceive? Each advance in our understanding of the cosmos opens the door to a universe of questions waiting to be discovered. And let us not forget the role of philosophy in this exploration. Fossil waves not only tell us about matter and energy, they also lead us to reflect on our existence and our place in the universe. What does it mean for us as human beings to understand that we come from an expanding universe full of mysteries yet to be solved? The next decade promises to be exciting. With projects like the James Webb Space Telescope and other missions in development, the horizon is filled with possibilities. What new wonders of the universe will be revealed in the coming years? The combination of advanced technology and human ingenuity could lead to surprising discoveries. Finally, research on fossil waves is a journey shared by all. Each discovery has the potential to change our view of the cosmos and of ourselves. Are we ready to face what comes and embrace the wonders we have yet to find? The universe has much to tell, and we, with our tools and curiosity, are here to listen. Cosmic background radiation, those echoes of the primordial universe, offer us a fascinating window into understanding our existence and the cosmos as a whole. What implications does this have for our perception of the universe? Cosmic background radiation not only tells us about the past, but also invites us to reflect on our own nature and place in the vast fabric of the cosmos. Consider for a moment the concept of creation. For millennia, various cultures have attempted to explain how everything began. Cosmic background radiation, with its origin in the Big Bang, provides tangible evidence of that moment. Isn't it amazing to think that the radiation surrounding us today is an echo of the explosion that gave rise to everything we know? It's as if the universe is whispering secrets to those who are willing to listen. When observing cosmic background radiation, we are confronted with profound questions about reality itself. What does it really mean to be part of a constantly expanding universe? This idea of expansion and change leads us to question our own existence. If the universe has been in motion since its creation, what role do we play in this cosmic story? The exploration of quantum physics, which intertwines with the study of cosmic background radiation, adds more layers to this philosophical discussion. The laws governing the behavior of subatomic particles suggest that reality is not as solid as it seems. Could it be that our understanding of the universe is merely an illusion built on a foundation of probabilities and fluctuations? This perspective invites us to rethink not only our view of the cosmos, but also our understanding of matter and existence itself. The fluctuations in the density of the early universe, which led to the formation of structures like galaxies and clusters, also hold philosophical significance. These small irregularities arising from extremely chaotic conditions remind us that order can emerge from instability. Isn't this a reflection of our own lives? Amid chaos, we often find opportunities to grow and develop. Cosmic background radiation teaches us that the universe, like us, is not a place of perfection, but of constant evolution and change. When considering the large-scale structure of the universe, we encounter the question of how we fit into this vast scheme. The galaxies we see in the sky are not just groups of stars. They are communities that have flourished from those cosmic background waves. How does this affect our perception of what it means to be human? If we are part of a constantly expanding universe with connections that trace back to the beginnings of time, what does this tell us about our relationships and our search for meaning? The theory of cosmic inflation, which suggests that the universe expanded exponentially in its early moments, also invites reflection. What does this mean not only for cosmology, but for our understanding of time and space? The idea that everything we know may have emerged from an infinitesimal singularity leads us to contemplate the nature of what we consider real. Is time an illusion? Is space merely a construct of our minds? Cosmic background radiation pushes us to consider these questions. Dark matter and dark energy, invisible forces that shape the universe, also raise questions about what we cannot see. If 95% of the universe is composed of these mysterious entities, what does this mean for our worldview? It reminds us that human knowledge is limited and that there is always more to discover. The pursuit of truth becomes an endless journey where each answer leads to more questions. In this context, research on cosmic background radiation becomes an act of seeking not only knowledge but understanding. What lessons can we learn about life itself through the exploration of the cosmos? Cosmic background radiation shows us that, although we are a small part of a vast universe, our curiosity and desire to understand are in themselves, fundamental aspects of what it means to be human. Philosophy and science, often seen as separate disciplines, can intertwine in surprising ways. Understanding cosmic background radiation allows us to observe the intersection between these two worlds. It reminds us that science is not just about data and formulas. It is also about narratives, stories that connect us with the universe and with ourselves. Could it be that by studying the cosmos, we are actually exploring our own essence? The fascination with the universe and cosmic background radiation leads us to question our future. As we continue to unravel the secrets of the cosmos, what new ideas and perspectives will emerge? What challenges will we face? And how will our understanding of ourselves change? The exploration of the universe is an ongoing journey filled with possibilities and discoveries that can redefine our existence. Ultimately, cosmic background radiation is more than just remnants of the past. It is a constant reminder of our connection to the cosmos. It invites us to look up, to question, and to explore. On this path, we find not only answers, but also a deep appreciation for the beauty and complexity of the universe. What other wonders await us in this vast ocean of knowledge and mystery? The quest has just begun, and each of us has a role to play in this grand adventure. Fossil waves are like the echo of the Big Bang, resonating through time and space, telling us an amazing story about the origins of the universe. Throughout our exploration, we have seen how these waves are essential for understanding not only the cosmos, but also our own place within it. But what does this really mean for each of us? Why should we care about those ancient vibrations that originated billions of years ago? Every time we look at the stars in the night sky, we connect with that cosmic story. Fossil waves are like an ancient map that takes us to the most primitive moments of existence. They show us how the first galaxies formed, how stars grouped together, and how the universe has evolved into what we know today. Isn't it fascinating to think that a simple beam of light we see in the sky could be a window to the past? The importance of fossil waves lies in their ability to answer fundamental questions. How did it all begin? What conditions existed in those early moments after the Big Bang? Thanks to cosmic background radiation, which is a type of light that has traveled through the universe for eons, we can glimpse those crucial moments. This echo tells us a lot about the temperature, density, and composition of the universe in its early stages. Can you imagine being able to hear the voice of the universe in its first whispers? What is astonishing is that these waves reveal to us that the universe is not a static place, but a dynamic entity in constant change. Dark matter and dark energy, two concepts that may seem abstract, are actually key players in this story. Imagine that the universe is like a gigantic tide that rises and falls, and that these invisible forces guide the flow of that tide. Without them, the universe would be a very different place, and our galaxies might not have formed at all. The evolution of fossil waves from the Big Bang to today is a fascinating journey. By studying how these waves have changed over time, we get an idea of how the universe has changed. Every small change in these waves speaks to us about the forces that have acted upon the cosmos. What message are they sending us? What new secrets are still waiting to be discovered in the vast ocean of space? Through key experiments like the Planck and WMAP missions, scientists have been able to map these waves and unravel some of their mysteries. These cosmic explorers have gathered information that challenges our assumptions and leads us to rethink what we know about the creation and evolution of the universe. Have you ever imagined what it would be like to live in a universe without these discoveries? Fossil waves also open the door to deep philosophical questions. What does our place in the universe mean in light of this story? If the cosmos is so vast and ancient, what role do we play as human beings in this grand stage? Science and philosophy often walk hand in hand, and by exploring these questions, we realize that understanding the universe also means understanding ourselves. As we move into the future, research on fossil waves promises even more surprising revelations. New technologies and methods will allow us to listen and see beyond what we once thought possible. Each new discovery is like a piece of a puzzle that when fitted together, offers us a more complete picture of reality. What surprises await us in the coming decades? The intersections between cosmology and astrophysics are vast and exciting. Fossil waves not only speak to us about the past, but they also influence how we understand phenomena like black holes, star formation, and galaxy evolution. The beauty of science is that each answer leads us to new questions, and each discovery opens new doors to curiosity. Alternative theories about the universe invite us to think beyond the conventional. Some scientists challenge the traditional narrative and propose new ways of understanding the creation of the cosmos. What if everything we know so far is just a part of a much larger story? Imagine a universe full of possibilities where our current ideas are just the beginning. As we conclude this journey through fossil waves, it is essential to reflect on what we have learned. These waves are more than mere vibrations. They are the remnants of a primordial era that connects us to the very fabric of the cosmos. They remind us that every star, every planet, and every being that inhabits this universe is part of a much broader story. Isn't it comforting to think that we are part of something so grand and ancient? Fossil waves teach us about the fragility and strength of the universe. As we advance in our understanding, we realize that the cosmos is full of mysteries that are still waiting to be unveiled. Each discovery, each question, brings us one step closer to understanding not only the universe, but also our own existence. So, as we look up at the sky, let us remember that we are listening to the echo of the past, that each star is a beacon of knowledge, and that through fossil waves we have begun to unravel the greatest story ever told. What other secrets does the universe hold for us? The search for answers continues, and each of us is part of this exciting adventure.